Good afternoon, everyone. It's a great honor and pleasure to speak at Brookhaven Lecture. I believe you know my name very well now, so let's get started without saying the name again. Today I will talk about a new technology developed by our group dedicated for a specific disease called prostate cancer. So given the unique feature of our technology, I believe it will lead the diagnosis of prostate cancer into a new horizon. Today, I welcome you to join me to take a trip to see what happened just before the sunrise. So, people may ask a question, why do we care about prostate cancer? So prostate cancer is the second common disease in men in the United States, in North America. So just behind the skin cancer. According to American Cancer Societies, 1 in 7 men will develop the disease in his life. In just past year, we have 230,000 patients diagnosed with this disease. Prostate cancer is also the second major cause of cancer deaths. So we know that prostate cancer most likely it will grow very slowly, but sometimes the cancer can be very aggressive. Again, according to American Cancer Society, 1 in 38 men will die of this disease. In the past year, we got 27,000 patients died. But the early detection of the disease is limited today by the available methods. So we'll go over all the methods today to see their limitations. Because of that, the most effective treatment of the disease today is still the surgical intervention. And a new method for diagnosis of the disease is highly demanded by the community. So here is the itinerary of our trip. So we will start with an introduction of prostate and prostate cancer. Then I will go over all the methods available today for diagnosis for cancer and focus on their limitation in terms of early detection of the disease and the accuracy. Then we'll get to the main part of this talk. We'll see the technology we developed, and we'll have the chance to see the engineering. We'll have the chance to see the engineering design, as well as the performance in the laboratory tests and the clinical trials. So in the last session of the talk, I will talk about a little bit about the improvement we are working on, try to make this technology better. And also, most importantly, we'll talk about our plan to reach the final goal in this research. So let's start with the prostate and prostate cancer. So at this point, I want to mention, as Susan said, I'm an electrical engineer, not a physician. And my job in this project is mainly for working on the developed instrument, and including the electronic designs and software development. That's in the early phase. In the later phase of this project, I collaborate with outside contractors for several things. For example, work with the safety test people to do the electrical safety test for the device. I also work with the medical imaging physics to try to evaluate the performance of the imaging performance of the device. And later I worked with the physicians to provide training to them before they do the clinical trials. So with that being said, I try to make the medical information in this talk very concise and to the point. So if you want to learn more detailed information, I suggest the website for American Cancer Society and the Prostate Cancer Foundations. They provide much detailed information. So prostate cancer is part of the reproductive system in men. So it's located right underneath the bladder and in front of the rectum. So, and it surrounds the urethra. So the healthy prostate is about the size of a walnut. So anatomically, the prostate is divided into three zones. So this is the transition zone, surrounds the opening of the urethra into the bladder. And this one is the central zone, and here is the peripheral zone. So peripheral zone is the largest zone in the prostate. It's the closest one to the rectum wall. During the physical exam, the doctors can put the finger in the rectum and feel this zone easily. But for the other two zones are very difficult or almost impossible. So we know all the cancers start from the abnormal cells. They can invade and damage the normal cells as well. From the name of prostate cancer, we can know the prostate cancer starts from the prostate cells. Specifically, it starts from the gland cells that proceed. These cells produce the liquid in the semen. This chart shows you that the pattern we'll see when we examine the prostate tissues under the microscope. So at the very beginning, for the normal tissue or at the very beginning of the prostate cancers, we can see all the gland cells are small and distributed uniformly on the microscope. When the cancer is growing into the advanced stage, the gland cells are separated from each other, and also the shape of the cells are changed. At the very advanced stage of prostate cancer, we hardly to see the gland cells anymore. So this is the pattern the physicians use in the biopsy procedures. Basically, the doctor will take sample from the prostate and examine the samples on the microscope and compare with this chart. Depending on the similarities, the physician will give the scores we call the Gleason scores. So Gleason score is a very important parameters in evaluation of the prostate cancers. I want to say that the causes of the prostate cancer is unknown as of today. Because of that, the prevention of the disease is impossible. So what we can do is just try to detect the cancer at the early stage and treat it effectively. And at the same time, we can minimize the side effect of treatments. Since we are talking about the early detection of the disease, we need to know a little bit about the prostate cancer staging. There are several systems used for prostate cancer staging. The most widely used one is called the TNM staging system, developed by the American Joint Committee on Cancer. Under this system, the physicians basically looking for the cancers and characterize them in 3 different locations. The first one, the T means the primary tumor, means the tumor is confined in the prostate and the nearby organs. N is the spread of the cancer into the lymph node, and M is spread of the cancer into the distant organs. So once we have the examination result from under the TNM staging system, the physician can give a overall staging number start from 1 to 4, depending on the TNM staging system, and also the blood test result and the Gleason score. So what we need to do is we want to detect the prostate at early stage when, for example, the stage 1, when the tumors are small and confined within the prostate gland. Now let's go over all the methods we have today for prostate cancer diagnosis. First, we start from the cancer screening. For prostate cancer screening, there are 2 methods. The first one is called blood test. It's basically the doctor will take a small amount of samples, the blood sample from the patient, and measure the prostatic specific antigen or PSA levels in the blood. If the patient has elevated PSA levels, then the doctor will do a physical exam. He put in the finger in the rectum and feel the hard core or hard areas in the prostate gland. If the cancer is found in either one or both of these processes, then the doctor, basically the cancer is in the early stages. It's a more treatable stage than if no screening were done. But the problem we have is either a PSA or DRE, they are not accurate. For example, for the PSA test, it has very high false alarm rate. We have 30% of patients with high PSA levels, but they don't have cancer. On the other hand, we have 15% of patients, we have very low PSA level, but they still have the cancer. For DRE, digital rectal exam, as I mentioned earlier, that the doctor can only feel the one zone, the peripheral zones. If the cancer is in the other 2 zones, so basically the doctor, basically in the physical exam, they just missed. So anyway, if one or both screening procedure gave you a positive result, then the doctor will prescribe more tests to confirm the disease. As of today, the gold standard to confirm the prostate cancer disease is still the biopsy. Before we go into biopsy, we need to know about ultrasound imaging, transrectal ultrasound imaging, we call it TRUS. Well, in this imaging procedure, what the physician does is he put a probe in the rectum. The probe will emit a sound wave. The wave will propagate into the prostate and echo back by the tissue and also the cancer tissue. Then there is a sensor in the probe can pick up the echo signals and send to the computer to make image of the prostate. The problem with the TRUS imaging is the ultrasound cannot distinguish benign and tumors. But ultrasound can provide a very clear picture of the prostate boundary. So we can use that information to do the biopsy. In the biopsy, the physician will put in a needle. Basically, there are two ways. One is the needle will go along the probe and go through the rectum wall and take sample from the prostate. Or the needle can go through a external hardware support, and put in the prostate and take sample. We call this one, this is a transrectal biopsy. This is a transperineal biopsy. Once from the ultrasound image, we find the boundary of the prostate, then we can take samples. So physician can take 6 samples up to 18 samples. The red circle here means the six sample procedure. The blue one is the 12 sample procedure, and the green one is the 18 sample procedure. So as of today, the most widely used one is 12 samples, the blue one. We can see if we have a small tumors between any two adjacent sampling point. So this tumor basically is missed in the biopsy procedure. This is one issue with the TRUS-guided biopsy. The other problem we have is if we have a tumor with the irregular shape, so we cannot guarantee the needle will go all the way through the longest dimension in the tumor. In that case, the size of the tumor is unestimated. We'll show the result later for this problem. So people may say, let's take more samples. So yes, we can take more samples, but keep in mind, the biopsy procedure is very painful to the patient. It can cause bleeding and also infection. So the best way to do that is we develop a new imaging procedure as a guidance for the biopsy. So we'll get back to this point in the later of this talk. Now let's go to see the imaging modalities that can be used for cancer diagnosis. Imaging technology are very useful in cancer diagnosis for a certain kind of cancer. But in terms of the prostate cancer diagnosis, we will see none of them are suitable. So I list mostly used modality here. We start from the first one is computed topography. We call it CAT scan or CT. In this technology, the CT image the organ or a tissue by measure the attenuation of X-ray that goes through the body. But as we saw in the past slides, the prostate is a very small organ, and it contains the soft tissue. Because of that, the prostate doesn't attenuate X-ray a lot. So the problem we have is the prostate doesn't create a significant contrast in the X-ray imaging. Because of that, the CT image is not suitable for prostate cancer imaging. And then the second one is MRI. is magnetic resonance imaging. MRI uses the radio frequency and the high, very strong magnetic field to image the organ or tissue. MRI does work for the prostate. It can image soft tissue, give a much clearer picture than the CT. This is one example of the MRI image. The problem with MRI imaging is it cannot distinguish the tumor and the inflammation area and also the blood product. For example, if you can see this is the prostate. We have the dark area here and here, but we cannot tell which one is tumor or which one is inflammation area. The rest of the imaging technique are nuclear medical imaging. So nuclear medical imaging is rely on the measure the distribution of radioactive tracers in a specific organ. And depending on the tracer we used, there are several different modalities. The first one we want to look at is a single photon emitted computed emission computed topography, we call SPECT. In SPECT, we use the radioactive tracer that target prostate cancer directly. Actually, the SPECT worked for prostate, but the biggest problem with SPECT is the SPECT system will look like this. So basically, we slide patient into the hole here, and this is the image, the gamma ray radiation detectors. So we can see the sensor is far away from the patient. So maybe it's 50 or 60 centimeter away. So because of the long distance, the SPECT imaging gave a very modest spatial resolution. Since the prostate is small, so we cannot see the tumor clearly in the imaging of the SPECT imaging. The second modality is the bone scan. Bone scan uses the same scanner like a SPECT. The difference is that for bone scan, we use a different drug. This drug will target the bone, especially the site invaded by the cancer. So this image shows you the bone scan image. We can see the dark area. That's where the cancer has spread to. So unfortunately, this is the cancer is in a very advanced stage. It's very hard to treat. The last one we want to mention here is PET images, position emission topography. So PET imaging, most popularly used PET imaging tracer is FDG. So FDG actually was developed by Brookhaven. And FDG is a glucose-based drug tracer. But for prostate cancers are not glucose dependent. So because of that, the PET imaging is not suitable for prostate cancer either. So this chart tries to summarize all the imaging modality we have today. In this chart, we have on the x-axis, we have the early detection. So in this end, we have the high likelihood for early detection of the cancer. And in the vertical axis, we have the spatial resolutions. So we can see all the method we have today is located on the left side of this chart, means it cannot be used for early detection of the cancer, although some of them have high spatial resolutions. So what we really want to do is we need some new method in this area which can provide early detection, for early detection of the cancer. At the same time, it provides high spatial resolution, so we can see the cancer clearly. So that's the transrectal gamma ray imaging we are talking about. So this will be the main part of this talk, to see the technology developed by our group. So our idea is basically we want to design a compact digital camera so we can insert it into the rectum as a probe. In this way, we can bring the radiation sensors right against the rectum wall. In that close distance, we can image the prostate very clearly. So we expect this device have several features. First of all, is the nuclear medical imaging device. We'll talk about it in the next slides about this. We also want the device to be compact, so it can work as a probe. Of course, we want the high spatial resolution so that we can see small tumors. And we want to have high sensitivities as well. The last feature is low cost. That means we, in addition to use our technology in the big hospital or medical center, we want to bring this technology into the clinics of a urologist so it can benefit all the patients. So in order to build such a device, we realize we need two key components. One is the radiation detector. The other one is application-specific integrated circuit. Before we look into these two key components, let's look at the medical imaging first. So we need to learn a little bit about the several concepts. Mainly is the radioactive tracer. So what's the radioactive tracer? So radioactive tracer is basically it's just a chemical compound. So depending on the chemistry of this compound, so the tracer will participate in a specific metabolic process. Because of that, the tracer will concentrate in the appropriate organ or tissue. Let's take an example, the iodine. Iodine is used in the production for the thyroid hormone, and so the iodine is concentrated in the thyroid. So what's the radioactive tracer? In the radioactive tracer, we need to replace one or more elements in the compound by radioactive isotope. We know iodine has one isotope, it's iodine-123. This one gives the gamma ray, emit gamma rays at 159 keV. So if we replace the natural iodine with iodine-123 and give this one to the patient, then the iodine will focus on the thyroid, will concentrate in the thyroid, then we can take image of the thyroid. That's the image we take. For this gamma ray imaging, we can see the two lobes of the thyroid. Because the radioactive tracer participates in a specific metabolic process, we call the nuclear medical imaging is the functional imaging because it can image the function of the organ instead of just give the anatomical information. And also because all the tracers have a focus on a specific disease, there are many tracers being developed for different disease in the organ. Now let's look at the concept of gamma camera. So suppose we have a organ like a prostate. Then we have the radioactive tracer focus in one small region, like we call the hotspot. So the tracer in this small hotspot will decay and emit gamma rays in all directions. If we have a pixelated detectors to detect gamma ray, this detector just very similar to the imaging sensor in the digital camera maybe in your smartphone. So you can think about that in that way. But we cannot use the detector to image this hotspot directly because the gamma ray will be shining on all the pixels. So basically, we just get a flat image. So we need something between them that will be a collimator. A collimator is a high-dense material with many parallel holes in it. It's the most simple design. So this is a cross-section of the collimator. We can see when the hotspots emit gamma rays for the one hole right underneath the hotspots, so all the gamma rays go into this hole, will go through it and detected by a pixel. For the adjacent holes and pixels, you see the gamma rays go in, and some of them are stopped by the receptors between the two holes, but a few of them will go through and detected by the pixel underneath that. And for the other pixels and the holes going further away, so the gamma rays doesn't go through anymore. So in this way, the collimator helps us to localize the hotspots into a few pixels right underneath it. Using this technology, we can take an image of the hotspots. Since we mentioned the radiation detectors, we need to learn how we can build the radiation detectors. So basically, there are two kinds of material we can use for for radiation detections. One is a scintillator, one is a semiconductor-based radiation detector. So scientilator detector has been used by industry for medical imaging for decades. So the way it works is, suppose this is the gamma ray beam coming in, hit the scintillation materials. In the interaction point, they will emit the light. The light will be emitted in all directions. On the one surface of the scintillation material, we attach another device called a light sensing device. The light sensing device can be a photomultiplier in a few inches size. And recently it come in a new one, like a silicon-based photomultiplier. That one can be in a few millimeter size, very small. So this device will convert light into electrical signals, and then the signal will be processed by the radar electronics. So the issue with the scintillator material is, so because the light is spread out in all the directions, so we lose the spatial resolutions. Although we have very shiny, very shallow beam, X-ray gamma ray beam coming in, but when we look at the profile, it's very broad. The other issue is we can only detect a portion of the light. The process of the light, the portion of the light going into this surface being detected by the light sensing device is kind of a random process. Because of that, the energy resolution of a scintillator is also poor. So now let's look at the semiconductor detectors. So in the semiconductor detectors, the gamma ray coming in interact with the material, then convert to electron charge directly. Then we can, since we apply the high voltage on these two surfaces of the detectors, with the electrical field, the charge will drift to one electrode on this surface. Then we can collect all the charge. We can see during the drift of the electrons, the cluster of the electron doesn't spread out in the horizontal directions, so we can maintain the spatial resolution. And at the same time, since all the charge will drift in one direction, we can collect all the charge, then we can also maintain a high energy resolution. Because of the advantages of semiconductor detectors, we select this device, this material for our application. Specifically, we selected cadmium zinc telluride, or CZT detectors. So our group, the radiation detector R&D group, has been working in this field on the CZT detectors for 50 years. So basically, we are funded by DOE in this research for national security purposes. But we also found this material has very good opportunity in the application of medical imaging because it has very good material properties. For example, it has a high density and a high atomic number. Because of this, so they have very high efficiency in stopping and detecting the gamma rays. So we just need a few millimeters thick detectors. We can stop almost all the gamma rays that being emitted by the isotope used in medical imaging. This material also has high resistivity, so that means the leakage current is low. We don't need to cool down this device. We can use this one in room temperature, because sometimes the cooling system can be very bulky. Of course, because CZT is also semiconductor, so we can maintain a high energy resolution and a spatial resolution. Now let's look at the other key component is application-specific integrated circuit. Simply saying is ASIC. First of all, let's look at the integrated circuit. So if you are not familiar with integrated circuit, you can think about that one like a processor in your desktop. If you open the case, you will see the processor. This one shown from Intel. If you open the package, you will see a silicon circuit. silicon-based circuit. So it can be very compact, integrate many functions. For example, this small one can integrate like a billion transistors in it. When we talk about the application-specific integrated circuit, we use the same technology to build the processors. The only difference, we designed the ASIC, we designed the integrated circuit for a specific application. In our case, is to just read out the signal from the radiation detectors. And we can, in this chart, you see when this is the signal processing for the detector pixels. So we have the charge-sensitive amplifier to collect all the charge. Then we have the main amplifier to amplify the signal and also stretch out the pulse, make it longer so we can measure the amplitude more precisely. And follow that, we have the digital part to compare the energy, the amplitude of the signal to a threshold. If the signal go over a threshold, then we can count that and increase the counters by 1. Basically, that's the photo counting application. So this block diagram is to show you it's just for 1 pixels. If we have many pixels, we can simply duplicate these blocks and make the pixelated, make them for pixelated detectors applications. This photo show you this is the real ASIC we fabricated and put on a dollar bills. The actual size is 6.6 by 6.6 millimeter square. And it's contained 6,000 transistors. And this chip was developed by the instrumentation division. And just like we package the chip, package the processor in the desktop, we also package this chip into a small package, then we can use that one in our application. So the real package of this is just 12 by 12 millimeter square. Now we have the key component in our hands, then we can build the system. What we did is we made a printed circuit board. Then we attached the CDT detectors on top of the board. Then on the bottom side of the board, we attach our ASIC. And beside that, we also have a readout control logic. It's simply a microprocessor. We can read out signals from the ASIC, then communicate with the computer. So this is the photo of a real detector module we built for our application. So this is one side of the printed circuit board. You can see 2 CDT detectors. The total area is about 15 by 40 millimeter square. Each detector contains 6 by 8 pixels. Each pixel is 2.5 millimeters by 2.5 millimeters square. If you flip this printed circuit board, you will see the 2 ASICs we used. Each ASIC will read out 1 detectors. So compared to the CDT-based detector module, I have one photo show the scintillator-based detector module. So this is one scintillator, and it coupled to a silicon PM-based light sensing device. Then there is a readout ASIC for analog signal process, then there's a digital part. So the total, I want to say this is the most compact scintillator-based detector as of today, made by Philips. And the total stack, if we use the same size, same thickness for detectors, the total size of this one is about 20 to 30 millimeter. And our detector module is 7.5 millimeter thick. So this is the imaging, the probe we made. We package the detector modules into the probe in the very tip of this probe. The detector is about here. And here is a handle with, inside we have the power supplies. And this computer is used for the image acquisition. If you cut this end and see the cross sections, you will see something like this. So this is a collimator we mentioned before, and this is the CDT detectors. here is the printed circuit board in the last slides, and here is a cavity in the shielding for the room for the ASIC. So around all these components, we have the shielding. It's tungsten-based shieldings. So it's a very complicated design, especially the shieldings. So this is the whole imaging system. Here is the cart. We install the imaging console in one arm. Here's a robotic arm. We can hold the probe. So at the tip of this arm, we have the rotation stage. The reason we put in this one is we want to increase the field of view of the cameras. We'll talk about this one in a few minutes. So now we have the imaging device. We need to test it in the lab before we put this one into patient's body. So for this purpose, we built a prostate phantom. It basically is the test fixture. It looks like it's a cylindrical containers. It's the size a little bit bigger than the prostate. In the cap of the containers, we have 3 threaded holes. We can put in a small sphere source or sphere containers in different holes, and also we can control the length of the bar. Then we can mimic the prostate cancers in the prostate. So in this photo, I show we have 3 spheres here, here, and here with different size and the different positions along the axial to mimic the 3 prostate tumors in the prostate. With this prostate phantom, we can do several things. One is we can fill this container with water to mimic the tissue of the normal tissue in the prostate. And we can also, then we can fill this sphere with the radioactive tracers to mimic the prostate cancer. And we can also do a contrast by filling both the sphere and the container with the radioactive tracer. The reason we did that is because all the radioactive tracers are not perfect. So although we developed the tracers target a specific disease like prostate cancer, most likely the tracer will focus both the cancer tissue and also normal tissue. So depend on the concentration in the cancer tissue and the normal tissues, we define the contrast. So in this test, we fill a sphere with like a 4 millimeter size sphere. We fill this one with a radioactive tracer, which has the concentration 8 times higher than the normal tissue. That's the one we fill in the big container. Then we can repeat this test with 4:1 and the 2:1 ratio. So the first row of the image here is the raw image we collected for these 3 settings. We can see if we collect enough time, so the hotspots region have a similar contrast, similar counts. Then we can see in the rest of the area, because that's the background, you can see in the 2:1 case, we have very warm background. After we subtract the background, we can see in the 8:1 case, so the sphere source is focused. We can resolve the image, and it's also very focused. But the 2:1 case, so the image is getting bigger, it's getting blurry, and in the 2:1 case, the whole image is blurry. We cannot resolve the image. Then we repeat this test with a bigger sphere, is 8 millimeter. So in this case, after processing, after subtracting the background, we can see the hotspots can be resolved in all the images, even in the 2:1 case. So I want to mention here is the radioactive tracer we used in the clinical trials. It doesn't have a good performance for prostate cancer imaging. So ratio is most likely is between the 2:1 and the 4:1 in this range. But even in this case, our camera still can see the small tumors as 8 millimeter. Well, 8 millimeter is not the smallest one we can see. The reason is, when we did this test, we didn't find a smaller, like 5 millimeter sphere. That's the one we want to test because our detector is designed with the intrinsic spectral resolution of 5 millimeter. As I mentioned earlier, our detector had a small field of view. It's 15 by 40 millimeters square. So it's smaller than the prostate. So we need more shot to cover the whole gland. So in this slide, I show you two short movies. This one on the left side is this camera view facing up, and this is the prostate phantom. So we have the sphere source, or we call this, we can think about this one as a tumor. Then we rotate this phantom from here all the way to the up. So we can see the image, how the image change when the source is, when the hotspots at different location within the prostate. So we can see on the image, we can see the image of the hotspots going off the screen, out of the field of view, and come back to the same position, but with the lower contrast because the source is further away from the collimator, from the detector. Now, we want to do another experiment. Suppose we have a cancer at the very edge of the prostate. So then in this case, in order to increase field view, we need to rotate our camera. So we can see the image of the hotspots moving from one edge when we rotate the camera, then move to the center, then move to another to the edge on the opposite direction. So actually, we used these two short movies in the training to help the physicians to try to understand how the probe operates and how we can use that one in the clinical when we put this one in the patient body. So we built this device, and it was cleared by FDA. Actually, this is the first gamma camera authorized by FDA for endocavity imaging on the world. And right after that, we did clinical trials at Johns Hopkins University and the Radiological Associates at Sacramento. And in total, we saw 14 patients, and 10 of them have confirmed disease from the biopsy procedure. So these slides show you the imaging procedure of our device. So the tracer used is the Proxiscan, is indium-111 based radioactive tracer. That's the only one approved by FDA by the time for prostate cancer imaging by the time we did the clinical trials with the Proxiscan. And here is the imaging procedures we use. At the beginning, we have the biopsy to confirm the patient has a disease or not. And the real imaging procedure starts from the injection of radioactive tracers. And after that, we wait for 5 days to wait for the radioactive tracer concentrated in prostate cancer. And at the same time, we wash the body will wash out the residues in the blood. So on the day of imaging, we did SPECT CT for comparison study purposes. And right after that, we did Proxiscan imaging. Some patients, and after imaging, some patients also went to our prostatectomy. That means it's operation to get the prostate removed. In that case, we also did a pathology study. Basically, we diced the prostate gland into very thin slice and examine them on the microscope. So then we can use that data as a comparison to see how our imaging probe performs in the clinical. So as I mentioned earlier, our camera has a small field of view. We need to take 4 images to cover one prostate gland. So this is the sketch of the prostate gland. So first of all, we insert probe a little bit deeper and turn to the right to take one image. Then we tilt the device a little bit to the left side and take the second image. Then we pull out the device by 2 centimeter and take 30 images. Then we tilt it back to the original direction to take the last image. So this example, this slide show you an example from the clinical trials. This is the real data from the patient. So here I show the sketch of the prostate and also the biopsy data. Basically, this patient has 8 millimeter size tumor from the biopsy test on the right side, on his right side. On his left side, the doctor found focal high-grade prostatic interepithelial neoplasia. We call it high-grade pain. So high-grade pain is a kind of a abnormal growth of prostate gland cells, but it's not tumor. It only have 20% chance to develop into tumor. But anyhow, by the time of a biopsy, so the doctor didn't find the tumors on the patient's left side. Now let's look at the Proxiscan images, these 4 images. So the yellow colors means the high activities, detected high activities. And from here we can see the high uptake from the prostate. And the red color means lower counts. Since these 4 images are displayed in the same color scales, we have to develop a criteria we used how to evaluate these images. So what we did is we find a lower count regions in each images and define that as the background of that image. Then we increase by 30%, by 50%, and use that numbers as a threshold. If there is a region in the images go above the threshold, we define that region as a high uptake region. And then we estimate the size of that region and report that data to the physicians. So based on these criteria, we find a 50 millimeter size of the tumors on the right side and a 5 millimeter size tumors on the left side. And this patient also went to an operation to get the prostate removed. In that case, we were able to do the pathology studies. So pathology gave the results 80 millimeters on the patient's right side and 2 millimeters on the left side. So we can see the Proxiscan images, the result is much, much closer to the pathology compared to the biopsy. And here I also show the SPECT CT images of, this is the base mid region, is basically the cross-section from here. And this SPECT CT images is from the apex region, basically it's cut from here. So we can see this is the prostate. We can see some kind of a high uptake in the prostate, but we cannot estimate the size of that in the SPECT CT. So by saying that, we can conclude that the Proxiscan agreed with SPECT CT, but the Proxiscan can provide a better spatial resolution. So the summary of the clinical trials. The clinical trials gave a very encouraging result, and the Proxiscan can see the small tissues, small tumors, and it is also more accurate than the biopsy. At the same time, we want to say is the Proxiscan has better spatial resolution than the SPECT CT. That today, this is being used today by the physicians for prostate cancer imaging. The last point I want to say is the Proxiscan, the imaging device, the technology is accepted by the patients. We did a follow-up for all the patients after the Proxiscan imaging for 5 to 7 days. And among all the patients, only one patient reported the bleeding. And during his next visit, the doctors checked him and found the bleeding was caused by the hemorrhoid. It's not from the Proxiscan imaging procedure. Now let's look at the last section of this talk. we'll discuss how we can improve this technology and also our plan to reach the final goal in this research. So eventually, we want to do a gamma ray imaging guided biopsy. Here, this is a picture I showed before. Once we have the boundary of the prostate, if we have a small tumor here, so in addition, instead of taking the samples from all these points, why do we take sample directly from this site? So we can, since we have the gamma ray imaging, we found these tumors, so we can put in needle to take a sample from here right away. So in order to implement these technologies, we still need a few more features in our probe. So first of all, we need anatomical information. Because we need, this one will provide the size or the volume of the organs, and also provide a reference where we want to take a sample. Then we need a 3D gamma ray imaging, because right now the gamma ray, the imaging we take is still a 2D projections. So basically we miss the information in the third dimension. So in order to do the imaging guided biopsy, we still need the third dimension information from the gamma ray. And the last feature is we want to put in the mechanism for the biopsy. Let's look at the first one, the anatomical information. So in order to implement this one, we integrate ultrasound transducers in the probe. And this is a sketch of the probe. And this is the field view of the gamma ray imaging. At the tip of the probe, we have one ultrasound transducer, the convex array. So it can take image, the cross-section image of the prostate in this direction. Then we can translate the probe. Then we can, using this transducer, we can make the 3D, to measure the 3D volume of the prostate. We also integrate the second linear array on the back of the probe in the opposite directions. So using these linear transit arrays, we can rotate the probe and to make the 3D volume, to visualize the 3D volume of the prostate. And both transducers were designed by GE Healthcare, and as of today, we have built two prototypes of the new probe we call the Gamma Scout. Here is the picture of the new probe, and this is the first, the ultrasound window for the convex array. On the back, you can see another one, the linear array, the window for the linear array. And we also wrote a software for co-registration of a gamma ray image and ultrasound images. Let me show this movie here. So basically, oh, sorry. Let's repeat that. So basically, the gray color on the background is the ultrasound image, and the blue one on the foreground is the gamma ray images. Right now, we are preparing to submit another FDA application for this new device, and we are also in the discussion for the new clinical trials with this new device. Now let's talk about the 3D images used for the gamma ray. So on the left side, I show you how people do the 3D imaging in the traditional ways. That's being used in the current imaging system for the whole body imaging. So basically, you have a patient body or the organ you want to image. So here is suppose there is a hotspots, so immediate gamma rays. So first of all, you put the detector with the colorimeter here, take one shot of this one projection. Then you need to rotate the detector to the second position to take the projection from a different angle. You have to repeat all this process and take many, many different projections, or you have to have an array of the detectors arranged in this circle to take the images, take the different projections. So then after that, you can feed all the data from all these projections into the computer using a 3D reconstruction algorithm to make the 3D image. But I want to say is this method is not suitable for our application because once we insert probe in the rectum, so we have no option to rotate the probe around the prostate. So we came up with an idea is, suppose this is the original collimators with all the parallel holes facing up. We separate them into two groups. The R group covered the row 1, 3, 5. The L group covers 2, 4, 6. So the R group will be tilted to the right side with an angle. Then we tilt the other group into the opposite directions. In this case, so we can, in one shot, we will take two views of the organ. And the shaded area here is the 3D field view. We can feed the data from these two views into our algorithm, and then we can do the 3D reconstruction. So this picture show you is the Monte Carlo simulation result on the computers. It's basically we simulate 8 sphere source in the cube with a 5 millimeter distance. And this is a reconstruct image. We can see all these 8 sphere source. Finally, for biopsies, I think that this task is pretty straightforward. The picture I show here is the ultrasound image with the ultrasound probe for prostate. And this is the needle insertions guidance. So we can integrate the same mechanisms into our new probe once we have the 3D gamma ray with the 3D ultrasound integrated. So this probe is manufactured by the BK Medicals. They are part of a team in this project. So for this reason, I see this task is pretty straightforward. In addition to use this, our technology, the detector prostate ASIC, for prostate cancer diagnosis, we can also use the same technology for several different applications as I listed here. For example, we can, in addition to the diagnosis of prostate cancer, we can also use the device for the prostate cancer treatment, especially for the radiotherapy. We know in a radiotherapy, the physician will need to place the small radioactive seed into the prostate to kill the tumor. By using our technology, we can precisely pinpoint the tumor site, and also since the seed have the radioactive, we can also image the seed. In this case, we can put the seed right onto the tumor site so we can kill the tumors more effectively. So at this point, we have covered the prostate for the 50% of the populations. Actually, we can also use the technology for another 50% of the populations. That will be for the breast cancer imaging and for the ovarian cancer imaging. Breast cancer in women is as common as in the prostate cancer in men. And actually, the breast cancers, the survival rate is lower than the prostate cancer. So today in the clinics, the breast cancer in the screening process, they use mammography. Basically, that's X-ray based imaging. But that doesn't work well for the high-dense breast. But since our technology is based on the functional imaging, so it doesn't depend on the density of the breast. So this supposed can give a better imaging for breast. And actually, there are companies that started working in this area already, and they have released the system, their imaging system, a few years ago. And in addition to the prostate cancer and breast cancers, we can also use our imaging platform for all the other diseases, as I mentioned here. And in addition to disease diagnosis, we can also use our technology, for example, to improve the existing SPECT imaging system. In the current SPECT imaging system, if you try to image, let's say, from one patient to another patient, they may use different tracer. So different tracer can give you different gamma ray energies. Because of that, so the physician has to replace the collimator in the system very frequently. So depending on different application, you may have the, for example, high efficiency, low spatial resolution collimator, or you have to use the low efficiency, high spatial resolution collimator. But since our technology can give very high energy resolutions, so using that, and we can develop a new algorithm to compensate the blurring caused by the different energy of the gamma ray. So this is one area we're working on, and this is funded by NIH. And besides that, we also can use our technology for the animal imagings. For example, in the drug discovery. Or we can use this imaging system directly for the animal treatment. So one slide I show here is for the cat. The hypothyroid is a very common disease for cat. And so we can use our cameras to image the thyroid of the cats. Here we inject the technetium-99-based read-F tracer to the cat. Then we can take the image. This is the Proxiscan images. We can see the two lobes of the thyroid. And this is a normal one. And this is one with the disease. It's getting larger. It's about 2.3 centimeter size. And because it's heavier, it's dropping into the chest. So you can see that they are in the different positions. And this one is from the scintigraph images. You can just see these two very blurry images. So our Proxiscan can give much, much better imagery. Some takeaway message from this talk. So we developed an advanced technology that could redefine the prostate imaging. It's a molecular imaging-based technology using the novel detector technology plus the ASIC design. And this device will target the intraprostatic tumors for early detection, so we can directly address the major shortcoming of a conventional imaging method used today. This device can give you high sensitivity and high spatial resolution for imaging, and this device is also low cost. Today, every year we have 1.7 million prostate biopsy. I mean, the trust-guided biopsy. So if we can use our technology to increase the accuracy of these procedures, that will be a high impact to the community. Since we started this project, we have generated 4 patents. One has been granted, and the other 3 are being reviewed. And we also win a lot of awards. So at the end of the talk, I want to say this project has been a multiple disciplinary research team since the beginning. Without them, so we cannot go into today. And here is a picture. So I want to acknowledge all the collaborators and the colleagues from our department, Non-Proliferation and National Security Department, and also from instrumentation, and from CAD department. And we also have people working from technology commercialization office help us to prepare the patents. And Mike Fury, the research partnership office, help us to put the contract in place and also help us to manage these projects through the scope of this research. Finally, one sentence or 2 sentences to thank the Department of Energy Non-Proliferation Research and Development for the primary support on the CDT detector research, and also thanks Hyperdyne Imaging Technology for funding the research on the Proxiscan gamma camera. Thank you.
Why the indium is more specific for
Can you repeat again? Sorry.
So why does the India recognize, does it accumulate in the cancerous cells more than the non-cancerous cells?
Oh, that's a indium 111 based radioactive tracer. It's not a pure indium element. It's a compound. It's basically an antibody its antibody targets the prostate cancer.
Okay, we have time for one more. Okay, if not, oh.
What do you think, or what could you tell us, what makes the breakthrough in this research, why this could not be done like 10, 15 years ago, and why Brookhaven is a good place for this research?
Yeah, I think just...
Repeat the question.
Okay, can you repeat the question?
No, go ahead and say.
Oh, the question is why this technology cannot be done 15 years ago. So as I said in the talk, we need two key components. One is the CT detectors. That's the expertise from our group. And the other one is the ASIC. That's the expertise of instrumentation. Gianluigi is here.
Okay, so one more. Is there one more question?
Is it possible to make significant improvements in spatial resolution? And if so, how would you do that?
Yeah, this current version of this device using 2.5 millimeters, and the NIH grant we are working on is 1.6 millimeters. We can make a smaller one, go to like 1 millimeter, no problem. And actually, we need that one for the 3D camera imaging without losing the spatial resolution.
I think thank Yonggang one more time. We